Okay, now when the resistors are in parallel, let us see how to represent the individual resistors first. Let me take first resistor and its corresponding noise voltage. So this is R1 and noise voltage, let me call it EN1. And let's say there is second resistor which is in parallel with the first resistor. This is R2 and its corresponding noise voltage source is, let's say, En. Now whenever resistors are in parallel, we must convert the parallel combination of resistor and the noise voltage source which is in series. We must convert it in the form of a resistor and a parallel current source. So we will do that. We will convert this in the form of a current source in parallel with the resistor. So this is my R1 and the current that I will get, the current value, I'll call it IN1. And IN1 will be nothing but EN1 upon R1. You can simply apply source transformation and get this representation. That is also not needed because we are already expressed resistor in the form of a parallel current source which represents the noise. Similarly, for the second resistor, let's say the value is IN2 and corresponding resistor comes in parallel. I'll call it IR2. So now if you see, I can always combine the resistors in parallel. We know that the current sources in parallel can always be added and written in the form of single current source. Let me say that is IN, and all the resistors can be combined, and let's say that is R equivalent. We know that R equivalent will be nothing but parallel combination of R1 and R2. Now IN can be written as IN1 plus IN2, but I will again remind you that this is RMS values, like EN1, EN2, IN1, IN2 are RMS values, and whenever we have RMS values, we can't add them directly, but we can add the squares of the RMS values. So IN square will be nothing but IN1 square plus IN2 square. And if I want the value of IN, it will be nothing but under root IN1 square plus IN2 square. Now if you remember, we had written the expression for IN1 and IN2. IN1 was nothing but under root 4kTb G. G was nothing but the transconductance. Square of that will be 4kTb. And this time I'll write it as G1 because that's the transconductance for R1. IN2 square will be 4kTbG2. So if I add them, you can say it becomes 4kTbG1 plus G2. This looks similar to resistors in parallel, but it is different. Please note that when resistors are in series, we can add their values directly and call it R1 plus R2. But when resistors are in parallel, we can't add them directly, but I can add their inverses. That means if I find G1 which is 1 upon R1 and G2 which is 1 upon R2, then the total conductance will be nothing but G1 plus G2. So therefore we get IN square equal to 4kTb into G equivalent. So that's my expression of the equivalent current source. Now here G equivalent is nothing but G1 plus G2, which will be nothing but 1 upon R1 plus 1 upon R2. And G equivalent can also be written as 1 upon R equivalent. So you can see 1 upon R equivalent is 1 upon R1 plus 1 upon R2, which is precisely the equivalent resistance when two resistors are in parallel. So when two resistors are in parallel, you can consider the equivalent resistance to be R1 R2 upon R1 plus R2. So now we can also define the equivalent noise voltage. En square will be nothing but 4kTb. Instead of G equivalent, I will consider R equivalent, and R equivalent in this case is nothing but the parallel combination of resistors. So whenever resistors are in series and parallel, we can use these results that we have just now discussed to find out the overall noise voltage and noise current, whatever is required.